Hello, everyone, and welcome to another episode of PyTorch Community Voices, your weekly show for and by the PyTorch community. Every Wednesday, Jessica and I host guests who are building some really cool things with PyTorch, and today is no different. Um, a brief introduction. My name is Suraj. I work at Facebook as a developer advocate for Facebook AI. Jessica, do you want to?
Hey everyone, good to see you all again. So I'm also a developer advocate here at Facebook, focused on our AI and ML projects.
So today I'm really excited for the episode. We're going to be learning more about quantum machine learning. And honestly, that sounds straight out of science fiction, right, Jessica? But
Definitely.
there is no, it's news to me that there is no fiction here. And there's actually a whole lot of science that our guests today, Josh and Tom from PennyLane, are going to tell us about. Welcome, gentlemen.
Thanks. Nice to be here.
Tom, could you tell us a little bit about yourselves?
Sure. So, hey everyone. So I'm Tom. I work at Xanadu and I focus on PennyLane. So my role is a mixture of research and also software development. So on the research side, I'm answering questions like, if we have a quantum circuit, how can we differentiate it? How can we get the gradient? And then obviously on the software development side, it's kind of putting those features into PennyLane, which is our main library for quantum machine learning.
Josh, please introduce yourself to our viewers.
Hi everyone, my name is Josh and I'm a quantum software team lead at Xanadu and one of the lead developers on PennyLane, which is our open source Python library for quantum machine learning on real quantum hardware.
It's awesome. That's really exciting, and I'm really looking forward to the presentation today. Just a reminder to our viewers, this is a live show, so if something resonates with you or if you have any burning questions, don't hold back. Please use the comments to type them in, and we'll get to the questions after today's presentation. Tom and Josh, I had a question for you before we get started. As a PyTorch user who isn't terribly familiar with quantum physics, why should I be sitting up and taking note on this?
So maybe I can take this one. So obviously, Josh and I are kind of believers in quantum, and we're very excited about this technology. But really, I think it will be a disruptive technology in machine learning. Maybe not right now, it's still in development, but over the coming years. And I'd see it as potentially another tool that you can add to your tool chain. So maybe instead of training on GPU, certain models might be more suited to training on quantum computer.
All right, perfect. Excited. So, gentlemen, I'll let you take the stage, and I'll show ourselves out. The stage is all yours.
Thank you. So perhaps I can start quickly just with a introduction to PennyLane itself. So what we're doing with PennyLane is, and I'll get into this a bit more during the presentation, but what we want to do is we want to bring quantum machine learning to PyTorch. So PyTorch is this amazing ecosystem and library and framework for auto differentiation, neural networks, and machine learning. And what we want to do is we want to make that accessible. So anyone who's using PyTorch for machine learning, they can start to integrate quantum aspects into their models and prototype and play around and access quantum hardware. So just a very brief introduction, but so PennyLane's open source Python framework for differentiable quantum programming of near-term devices. So something that people might not be aware of is that quantum hardware is here today and it's accessible over the cloud. So you can go to various different providers who provide access to quantum as a service over the cloud. So at Xanadu, we provide Xanadu Quantum Cloud. So we have quantum hardware, specifically photonic hardware, that's available over the cloud. Other providers such as IBM, provide superconducting qubits over the cloud, IonQ, and various other companies provide this hardware today. So this is a really, really cool time to be developing quantum software and to be playing around with quantum machine learning, just because it's not theoretical. We can actually take these models and take these prototypes and play around with them right now. And so that's why we designed PennyLane. We designed PennyLane so that not only you can access these quantum hardware devices via Python and program them via Python, but you can also do it in a differentiable manner. So not only are you able to submit things and get results back, but you're able to extract the gradients. And because we can extract the gradients, we can integrate this into the machine learning toolchain. So what is quantum computing? So quantum computing is very unique. When you compare it to classical computing, the way that we're doing the computing is very, very different. So when I say very, very different, the underlying physics of the computation is quite different as well. So a lot of what we know from classical computation, we kind of have to rethink. Things such as being able to copy and paste states, which we do in classical computation, we can no longer do in quantum computation. Everything is reversible, everything is unitary. So there are restrictions and differences to how we look at quantum computation, but with those differences comes a lot of power. We have the ability to take into account quantum effects such as entanglement and superposition, and use this to do computations that wouldn't be accessible classically. So if you are interested in quantum computing, something that you might see, terms you might see appear again and again as you're reading into it, there are two terms really, quantum circuit and quantum gates, and I'll describe them in a bit more detail now. So this is a very high-level overview of what quantum computing looks like now. So this is the abstraction that we're currently working with when we're talking about quantum computing and quantum algorithms. So what you see here is we have a diagram, and on this diagram we have 3 qubits. So these are the horizontal lines. And the way you read this diagram is we're going from left to right. So we're starting in the side here in the all 0 states. We're propagating across the circuit down these lines, and these represent quantum particles. So we have a quantum particle here, here, and here. And what we want to do is we want to harness these quantum particles to do computation. And to do that, we apply gates to these qubits. And that's what these green boxes are. So we have our qubits in our system. We're applying some quantum operation to our qubits, and we can even apply quantum operations that interact qubits. So we're taking these quantum particles and we're making them interact, and we're creating entanglement, and we're creating superposition. And this is really where the power of quantum computation comes. So we've interacted our quantum particles, and then once we've done that, we measure the output of our quantum system. So now we want to see, after we've added our quantum gates and operators on our qubits, what is the final state of our quantum system? So we measure the quantum circuit, and this gives us classical data coming out that we can then use as to view the result in the way of our computation. So how does this relate to quantum machine learning? So let's zoom out a bit. So in the previous slide, we're looking very low level at an abstraction of what's happening on the quantum hardware itself. But what we can do is we can treat this almost like a black box. And that's what we're doing here. So we've still got a quantum circuit, but now we're just thinking of this as a function, u of theta. And those quantum gates that we were applying to our quantum system, we can think of those as parameterized operations. And these are operations that yes, we're applying them to quantum particles, but they are classically controlled. So in our labs, whether it's a photonic lab or a superconducting qubit lab, we're using control hardware to tune these operations as they're applied to our quantum system. And we're using continuous classical parameters to tune these operations. So that's what this theta is here. We have a black box, but we're able to set the parameters of this black box. So that's what theta is. X is the initial state of our system. So in the previous slide, I mentioned that we have our quantum circuit and we have our qubits in some initial state. We also have the ability to prepare that initial state. And that's another degree of freedom we have. So we have our state preparation, we have the parameters of our quantum operations, and then we perform our measurement and we get classical output out of that. So from another perspective, this almost looks like a neuron or a node in the neural network. We have classical data coming in, continuous data coming in, and we have continuous data coming out. The key insight is we can actually differentiate this, and we can differentiate that on the quantum hardware. And so this really unlocks something powerful. It unlocks the ability to train a quantum computer like we train a neural network. So that's essentially the idea of PennyLane. We unlock the ability to not only access this quantum hardware, but train this quantum hardware and integrate that training into frameworks such as PyTorch. So that's just what's represented here. On the left-hand side, we have a quantum circuit with some parameterized operations. Some of them have fixed parameters, so these gates all have pi and 4, whereas this layer here, they're freely parameterizable. And these input parameters, theta 2, theta 3, theta 4, etc., that could be input from the circuit, perhaps from a classical neural network. So you have a neural network in PyTorch that's generating these weights. They input to this quantum layer here. We perform some entanglement, we do some measurement, and then the output of that is returned to PyTorch. And what we get from this sort of architecture is we get the ability to integrate optimization landscapes and cost functions into our classical models that potentially are not accessible in a purely classical framework. So I mentioned this slightly before, but the big thing that PennyLane provides is this ability to interface with PyTorch. So I said that it provides the ability to integrate your quantum models into your classical models in such a way that gradient descent and all those gradient descent workhorse algorithms that we use in classical machine learning are accessible. Thinking about it from another perspective, another way of saying the same thing is that PennyLane, in essence, makes PyTorch quantum aware. So when you're using PyTorch currently, you have the ability to deploy your models onto CPUs and GPUs. Using PennyLane, you also have the ability to include QPUs or quantum processing units into your workflow. And it does this seamlessly, and it connects to quantum hardware. And from PyTorch's point of view, it's back propagating through a standard classical model, but it comes to a quantum component, and PennyLane will then dispatch to the quantum hardware, compute the gradient, and return that to PyTorch. So this works from a very low level, but it also works from a higher level abstraction in that you can create torch.nn quantum layers using PennyLane. And Tom will discuss that a bit more coming up. So you can use PennyLane to seamlessly integrate quantum hardware into your classical machine learning models. But you also have the ability to seamlessly integrate hardware from across the spectrum of available quantum hardware. So you can integrate hardware that's coming from IBM, hardware that's coming from Google, Rigetti. In addition, you have the ability to combine different types of quantum hardware into a single model. So we're at that point in the quantum computing industry where hardware is not all interchangeable. There are some quantum computing hardware and models that have advantages compared to other. So PennyLane doesn't restrict you to one type. You have the ability to pick and choose and maybe use more than one that have different strengths for different areas. So now I might pass over to Tom, who has a taster demo to share with you.
Thanks, Josh. So just give me a second to share my screen. So stop me if you can't see this. Cool. So I have a taster demo. Actually, I didn't need to go into the slides. It's just here. So the idea here is just to actually show you some PennyLane code, get our hands dirty, and see how things look. So what we're going to do is we are going to do a very simple model of classification of the moon's data set, using a model that's a hybrid, so partly classical and partly quantum. So yeah, let's have a go. So usual inputs that you might expect, things like Torch, of course, and then scikit-learn. We're also, so this is the new thing, we're also importing PennyLane, of course. So now let's get our data set up. So we have this sort of 2 interleaved moons as our data set, and we need to classify between the two classes. So the key step for making this hybrid model is to design the quantum element of the model. So what does our quantum circuit look like? And this is the first bit of PennyLane code that you'll be seeing. So in this cell here. And we have a couple of elements. So the first thing you typically see is picking a device. So the device is the thing that executes the circuit, and that so you feed a circuit to a device and it gives you the answer, the output measurement from the circuit. So there's a variety of different devices, as Josh mentioned. So you could have simulators. You could also have hardware, of course, so on IBM, AWS, etc. Here we're just using a standard simulator, just for a quick prototype. So you'll see typical PennyLane code loads the device and also loads up a circuit, which we often call a Q node in PennyLane. I won't go too much into the details of the contents of the circuit, but you can think of it as, so these templates are kind of a fixed arrangement of these gates to a certain depth. So we actually have a layers parameter, which is saying that we repeat fixed layers of these gates that are all parameterized and controllable. So this is the circuit here. We also have a measurement. And what we do is we bind our circuit to the device. So we have this decorator that takes the circuit and says that you're going to run on this device, and also picks an interface. So we say, let's output the results of our circuit as a Torch compatible tensor. So, okay, we've now loaded our device and our circuit. Let's have a little bit of a play around with how it looks to interact with this. So here we load some example inputs. Just nothing too dramatic, just some ones and some random numbers for the input to our circuit and the weights. So we load it here. And now this cell, this is evaluating our quantum circuit for some given inputs and trainable parameters. And you can see we get some 2-dimensional output. The dimension here is, of course, determined by how many measurements we do in our circuit. So this is evaluating the circuit, but of course, we want to train. So we want to vary these trainable weights here. And to do that, we need the gradient, of course. So how can we get that? Well, this next cell where we load up. So this is just a very simple cost function just to get, I guess, a single number to come out of our Q node. So we just add up the outputs measurements of our Q node. Further down, we'll actually have a more informative cost function. So now what we can do again is evaluate our cost function for our trainable, so for our inputs and our trainable parameters. And now it's just familiar PyTorch. So you can call the backward step, and you can look at, now you can find the gradient of these parameters, which is what we have here. So this is just showing you how to evaluate a circuit and how to find its gradient. Let's actually use it for a sort of prototype task, which is the classification of the moon's data set. So what we're going to do is combine our quantum circuit into a hybrid model. The hybrid model you can see just here. And again, super simple, just really for the idea of showing off rather than being competitive with the best problems and neural networks out there. So it's just a very simple model. We have a 2-neuron layer that takes the input data. We also have a 2-neuron classical output layer and a softmax on top of that. And in between that is sandwiched our quantum circuit that we just defined above. So we have these multiple quantum layers within this sort of, as you can see, the circuit layer. There's 6 of these, all within this quantum node. So how do we set this up? Well, you can see here we're plugging in our circuit to torch.nn, to the torch.nn module. we're converting our Q node, our quantum circuit, to a torch layer. So by doing so, it really, from sort of Torch's perspective, it really just looks like another neural network layer. Under the hood, of course, it's a quantum circuit, but in terms of the, say, training this model, it's then just, you can evaluate it and you can find its gradient. So now this cell is creating the bigger hybrid model. We have our input and output nodes and a softmax, and we use the torch.nn.sequential model. Cool. So once you've set this up, once you've got your model, it's just very standard, and it's very standard PyTorch. So it'll be stuff that you're familiar with. And so what's cool, right, is that you're able to use familiar tools in PyTorch, but actually also be training a quantum circuit, potentially on hardware, under the hood. So it's quite exciting, this ability to combine the two. So now we're going to train the model, and so we have just a standard optimization loop. We're running over 6 epochs, and you'll see, hopefully, you can see the loss being printed out. This should go down. So one thing to be aware is that speed is definitely something that we want to prioritize. So it's actually a little bit slow. It's a very simple network that should be, evaluating very quickly. But of course, there's now a quantum circuit included. And as you add qubits to your quantum circuit, it becomes exponentially hard to simulate. So obviously, on the quantum side, it's always a challenge to get as much speed. But just to explain to you why it's not evaluating, I guess, instantaneously. But anyway, you can see the loss function is going down. And yeah, we're successfully training on the Moon's data set. So hopefully now you've got a bit of familiarity with some PennyLane code. I guess the key parts are around here, defining the circuit, the device, the plugin to Torch. So I also, now you've seen a very simple example, the Moon's data set. I want to show you something a bit more, I guess, more ambitious and more interesting. So this is a research project that we did a while back with the aim of using a quantum circuit, a quantum network, for something a bit more practical, a bit more relevant to machine learning. So this research project was called quantum transfer learning. So let's take a step back and think about what we mean by transfer learning. And this, sorry if it's familiar to some of you already, but so just to explain, imagine you can see on this diagram here on the top right, you have some pre-trained network. You've got a certain data set and a certain task, and you've trained your network on this. So for example, maybe the data set is ImageNet, and we want to do classification. And our network might be, say, ResNet 18. So we've already trained, and we've got our model working successfully. Imagine now we have a slightly tweaked data set and task. It might still be classification, but maybe it's a different data set, or it's a subset of your current data set. And you want to now train on this task. What can you do? So one option is maybe you just start with a new network and you train again from the start. But another intuition is that we've already got this network A, this ResNet. It's already working nicely on a very similar task. Can we use the learning that we had from there to sort of transfer it to this new task? So the idea of transfer learning. And this is really what we do here. So we say, okay, you can chop off the last few layers of your train network, and you can add on a new network. So you combine to get this A primed and B. And then all you need to do is train for this new task, this TB, only train the B part of your network. So you need to vary those parameters, and you can keep A primed fixed. So the intuition, I guess, is that your network A was originally trained so that maybe the earlier layers were good at finding perhaps general patterns from the data. So maybe early layers were saying, okay, this is a certain shape. And then the later layers, maybe the last few, these are used to do the final classification part of the task. And that's the thing that we've swapped out. So likewise, we can swap out to a different network and then train B. So this is transfer learning, and it's an established thing. what we were looking at is this idea of quantum transfer learning. So instead of this B part now, instead of swapping it out for another classical neural network, what if we put in a quantum circuit? And this is, the idea is that, of course, quantum machine learning is still early days, and it can be difficult to scale the number of qubits, as I mentioned. So this is an idea of let's lean a little bit on a successful classical network and try and combine it with a smaller quantum circuit and see if we can do something practical. So it's a classical to quantum transfer learning. So what we did particularly in this paper, in this project, was to train on this Hymenoptera data set. So it's this data set of ants and bees. So how did it go? Well, yeah, it went well. You can check out the paper. It's listed down in the bottom here, and I can also send it. I guess we can send it as a message. And yeah, you can see the accuracy in the top right here of this hybrid network, depending on so you can execute the quantum circuit on, of course, simulator or hardware. So this is the column here. Did we run it on simulator, on IBM hardware, or also on Rigetti hardware? You can see the corresponding accuracies. So of course, hardware is is currently a bit limited. You can have errors. So we see the accuracy go down a little bit versus the simulator-based accuracy. But it's still a nice proof of concept that you're able to get a hybrid network that's partially running on quantum hardware to train on an actually relevant and interesting task. And of course, all this was using PyTorch. So we were using PyTorch for loading the data and also setting up this hybrid network and also training. So all of the elements we were using PyTorch. And you can check out the demo here. So this is the quantum transfer learning demo. It was based also on a very nice demo from the PyTorch team on transfer learning. So yeah, definitely thanks to the PyTorch team. So if you'd like to learn more, please check out our website, PennyLane.ai. We have a load of demos and tutorials that can take you from very basics, if you never really interacted with a quantum computer, to sort of the cutting edge of where the field is now. So thanks very much for listening. I guess this wraps up the sort of presentation part of the session. And I think we can open up for questions now.
Well, thank you so much, Tom and Josh, for that presentation. We have some questions already from the community, but I wanted to sort of just rewind a bit. So for those of you who are just joining us now, Tom and Josh from PennyLane just spoke to us about how you can run your PyTorch models on quantum hardware using PennyLane. It offers an abstraction where you can wrap quantum circuits in a torch.nn module, and it just runs as you'd expect a PyTorch module to run. Before we get to the questions from our audience, a quick question: how did the name PennyLane come across? Every time I read this, every time I go to the docs, the song starts playing in my head. Was that intentional?
Yeah, definitely. Well, I don't know whether officially, but certainly we're a fan of the Beatles. Yeah, so another one of our libraries is Strawberry Fields.
All right.
Which is the A side or the B side of the records. You had both sides, so the Strawberry Fields and PennyLane.
Yeah. Very cool.
And we have another library, the Walrus. So the Beatles theme continues throughout our quantum software.
Nice. That's a cool Easter egg to have. All right. First question from Ronnie Petson. Thank you, Ronnie Petson, for this. He wonders, how do you actually make these quantum circuits or quantum computations differentiable, especially when there's a lot of qubits involved?
So to take it, Josh?
This is a really, yeah, sure. This is a really good question. And it was an open question, I think, for a long time, in that I think when the people in the field of quantum computing started looking into using machine learning tools for quantum computation, a lot of the approach was that actually you build the simulation using an AutoDiff framework. So you build the simulation using PyTorch, for example. And if you write the actual classical simulation of the quantum computation, then as you apply the operations, PyTorch in the background is doing auto differentiation, and you get the gradient out of that. The problem is that this isn't scalable. It works really well for small simulations, but the amount of classical resources, the amount of memory required to simulate this grows exponentially as the number of qubits in your system grows. So what you really need to make a quantum computation differentiable is you need the ability not only to execute the circuits on hardware, which is what we had, but the ability to execute on hardware and also get the gradients at the same time. So ideally, we need a way of not just using quantum hardware to get the gradients, but using the same quantum hardware we used for the forward pass or the cost function evaluation. If we can reuse that same hardware device to also get the gradient, so we don't have to use additional qubits, we don't have to use very different circuits, but use what we have, then that's what sort of unlocks this power of using quantum hardware in a differentiable manner. So it's something that it's still quite new research in the field. It's something we've been doing a lot internally at Xanadu. And the idea here is that there are gradient shift formulas that have been in development over the last couple of years that allow you to take a circuit that you're evaluating on hardware, shift the parameters of the gates according to some particular rule for the operations on that circuit. And if you do the shifts correctly and then combine those results, you get the gradient. So that's a really, really nice result that sort of unlocks the differentiable quantum computation and sort of drives a lot of what PennyLane does behind the scenes. So PennyLane implements these quantum gradient rules and translates from the vector Jacobian products that PyTorch wants to these quantum gradient rules that are executed on hardware.
All right. Thanks, Ronnie Petson. Mahabubul asks, he asks a two-part question. Does PennyLane support A, the execution of quantum workloads on GPUs when used with PyTorch? And B, does it also support parallel computation of the gradients?
So for the GPU question, partially, I'd say. So currently, we have some level of GPU support, but actually what you really need is a device that's or a simulator that's really dedicated to running on GPUs. So that's something that we're missing, but it's something on our agenda to take on. And when that's available, yeah, you should be able to, I guess, evaluate gradients very quickly and integrate with PyTorch.
Right.
We can also answer the second part of the question as well. So parallel computation of gradients. So depending on how you evaluate the gradient, if you want to do, there's different rules. So there's the parameter shift rule is the one that Josh mentioned. And this is hardware compatible. So this is also suitable for parallelization, and we currently have support for that. So it involves evaluating multiple separate circuits. So it's very easy to parallelize. Josh, do you want to speak to any more of this?
Sure. So this is something we already do to some extent in PennyLane. So like Tom just mentioned, when you have a single circuit or a single quantum model that you want to find the gradient of, that corresponds to evaluating that same model lots of times, just with the parameter value shifted. And from that information, you get the gradient. The cool thing about this is those shifted evaluations, they're all independent from each other. You don't have to wait for the result from one before you can execute the other. So something we've integrated into PennyLane is that if you're using hardware that supports sending multiple circuits at once or multiple quantum algorithms at once, PennyLane will do that automatically behind the scenes. And so we're still in quite an early stage of quantum hardware access, but as that grows and as the industry grows, we'll likely be in a place where you might not just have one quantum hardware device available to you, but maybe hundreds or thousands of quantum hardware devices available. So you can actually farm out the computation of these gradients by using maybe 1,000 QPUs in parallel one for each parameter gradient you need, and then have the result returned to you over the cloud. So yeah, two really good questions, and both things that we're thinking of and in the process of supporting in PennyLane.
Sorry, I can't hear you, Suraj.
Sorry about that. Alan has a question about model interpretability. How do you do that with quantum machine learning? Is it very different from conventional GPU normal ML?
So I don't know, Josh, if you have a better answer, but I think my response is that this is evidence that it's such early days in the research field, right? So I genuinely don't have a good answer for interpretability. And you could probably do a PhD in it and sort of own that part of the field. So it's a very interesting question, and one that I'd be interested to see, but I'm not aware of how really to do it now.
I guess that really points to how new the field is, right? Like so many things are a green field even like at this moment, and it's definitely, there are so many research opportunities over here. Thanks, Alan, for bringing that point up. Emil has a question about the simulators. So he asks, PennyLane supports QLAX, which is a quantum simulator which already has support for running on GPUs. Is PennyLane taking advantage of that?
So I believe it does take advantage of that at the moment. If you've installed QLAX with GPU support, you should be able to access that device and have the quantum simulation part take place on the GPU. When thinking about using GPUs with quantum computations, it really depends on the model and the algorithm that you're building. If you've got lots of smaller quantum components in your model, and you're interfacing that with a bigger PyTorch model that uses a GPU, sometimes it makes more sense to use a quantum device that's written in PyTorch itself. So that way you're using the same, PyTorch is driving the entire simulation. You're not having to hand off between a separate quantum simulator and PyTorch, and you have the power of backpropagation to get the gradients. So I think it's something that's not big, because the field is so new. These rules of thumbs over like when to use GPU, what simulator should I use? Should I use backpropagation? Should I use this parameter shift rule that we use in the hardware? These are all very, very good questions, and yeah, it's not always clear the best pathway to get the best results. But yes, PennyLane does take advantage of GPUs on QLAX, and at the moment, we're also in the process of building a new PennyLane device called Default Qubit Torch. And what this does is it allows you to do simulations that are driven by Torch. And you have the power to do backpropagation with GPU support, and they should be a significant speed up when using this new device. So hopefully this should be available in the next PennyLane release or the release after.
If I may ask a rather noob question, you mentioned in your presentation that one of the significant advantages of using quantum hardware is that your algorithms can make use of entanglement and superposition. Can you break that down? Like what exactly does that mean? Does that mean faster algorithms? Does it mean more, I don't know, more accuracy or better precision?
Yes, I guess I kind of see there's two perspectives. There's a long-term and a short-term perspective, and it's all related to the progress on the hardware. So currently right now we're on tens of qubits, and they're noisy. What we're aiming for in the long run is to have thousands of qubits, and also for them to be fault tolerant. So if there is an error, you can correct this error. So in the long run, we have a whole host of interesting algorithms, quantum machine learning algorithms that can improve on machine learning. And what sort of improvements? So they're typically things like speedups. you might see exponential speedups or sort of polynomial quadratic related speedups. Also the ability to handle much larger data sets. So this is typically what we expect in the long run, more so in the near term. So when we have a question, right, of what can we do with these near-term devices that are a bit noisy with tens of qubits, and again, I guess I come back to it's still partially an open question, and you can see papers that are going sort of positive and negative in both directions. But I'd say that the gist of the idea and the intuition is that you might get a more flexible model. So by having this entanglement and superposition in your circuit, you might be able to, your circuit is effectively a function, right? And this function might be able to sort of represent or do transformations that you wouldn't be able to do with a classical network.
And if I may just follow up with another noob question. Is it accurate to consider the gates that you mentioned in the quantum circuits as analogous to the operators in a neural network? Like, for example, the most commonly used operators would be just your matrix multipliers or the nonlinearity operators. Is that something what we are going for when we add those angle embeddings, if I remember correctly, in the circuits? Are they similar to what we are doing with operators over here?
I think you can go down that perspective. And it would be ideal if we can think of just this quantum neural network as a matrix transformation, a nonlinearity, and then maybe something quantum somehow. So you can use that intuition, and often does help. You can say, oh, the circuit has a certain width. It's got some layers. So maybe that's like layers of a neural network. It's not an exact comparison. So it's not like necessarily there's a certain layer that is exactly equivalent to a matrix multiplication and a bias and a nonlinearity. So you can also fall down that trap. And so the intuition only goes so far. And yeah, I guess it's what are quantum circuits doing? And it's still open research, but we have perspectives on stuff like it does feature embedding. So you have some input feature space, and you end up embedding your data into a higher dimensional feature space that depends on the quantum circuits. And then you can take sort of the inner product between points in your embedded feature space. And the gates that you choose affect this transformation.
Okay. Right. I did also see on your website that you have something called community calls, which I believe is a co-hacking event. Can you tell us a little more about that?
So we have two sorts of events happening at the moment. So the first is that we have weekly community calls. These community calls, if you want more details, definitely check out our website, PennyLane.ai. I think we have a banner there with information on our blog with more details. They're hosted on, there's this great open source foundation in quantum software called the Unitary Fund. And they provide a really nice space for people who are exploring quantum software and want to get involved and want to contribute. Maybe they come from background in classical machine learning and just want to explore what they can do and what can be done with quantum machine learning and quantum software. So we have a weekly community call as part of the Unitary Fund community. And it's 1 hour where we present, once a week, we present a demo and maybe a new interesting feature in PennyLane or a tutorial on something cool you can do in PennyLane. And we also discuss things such as creating a PR and contributing back to the community or submitting a tutorial that uses PennyLane. Just because we want to encourage not just contributions to quantum software, but we want to encourage sort of diversity of voices in quantum software as well. At the moment, quantum software really is dominated by physicists. So Tom and I we both have physics backgrounds. There's the field of quantum software as a whole will just benefit so greatly from having people from very different diverse backgrounds providing input, like from things like how they want to be able to use quantum computers, to how quantum software can be made better in accessing quantum computers. So that's sort of an overview of our community calls. I believe they're at 11 a.m. Eastern time. So if anyone listening is curious, check out our website and our blog post, and there'll be a link there to join the Unitary Fund community to take part in those community calls. At the same time, we also have a event called Code Together. And what Code Together is, it's a virtual hacking event for about 2 weeks where interested participants and contributors can open PRs against the PennyLane repo, from things related to changes to documentation, to bug fixes, to new features, and merged PRs. The people who have PRs that are merged in will receive both, I think, digital swag, maybe physical swag as well. But we have another blog post and more information on our website about the Code Together as well.
And I think that's really essential, especially when the field is new and you really have the chance to pioneer the direction that it takes. That's pretty cool that you have avenues inviting people from different backgrounds to sort of contribute and learn along with you. Very cool. I encourage the viewers to whoever's interested to just go to their website. I saw this on their blog. It's pretty well elaborated over there. Definitely check it out. Switching gears a bit, we wanted to ask you, what do you think is, I mean, what's your favorite thing about PyTorch, or what is something that really made it easy for you to work with PyTorch, especially, I guess, integrating quantum circuit support in a library that's used conventionally for neural networks on GPUs?
So I can definitely speak from a developer perspective, but the thing that really works with PennyLane, the thing that makes PyTorch so easy to work with PennyLane from a developer point of view is that PyTorch has this great ability to define custom gradients. So if there's something, so say you have very unique hardware, in our case we have quantum hardware, or say you have a function that maybe doesn't work so well with backpropagation, maybe it's not stable, maybe it, the gradient has a significant error when you're using backpropagation. But PyTorch provides the ability to register a custom gradient function for that part of your model. And that's why it connects so well with PennyLane. What we do in PennyLane is we use this API to register a PyTorch custom gradient corresponding to a quantum function. And so when PyTorch is backpropagating through the model and it reaches this quantum function, because of this amazing custom gradient API, it's able to hand off to PennyLane, and PennyLane does the groundwork of computing the quantum gradients and doing the vector Jacobian products and returning it back. So definitely that's something I really love in PyTorch, maybe not something that most PyTorch users are familiar with. The other thing that, and I think this is more a recent thing, so PyTorch 1.5 onwards, but support for complex numbers. So I mentioned that we're in the process of releasing a quantum simulator that uses PyTorch as a backend. So you can do backpropagation GPU-powered backpropagation during your quantum simulation, which will be really, really powerful and really, really fast for a lot of workflows. And that's another thing that's been enabled by new features in PyTorch, such as complex number support.
I agree. The custom autograd functions really make it easy to extend PyTorch. And this is a really awesome example of where that's actually gone ahead and spawned an entirely new paradigm of deep learning. So really cool with that. And usually we ask our guests a final question of what they're looking forward in machine learning. But I'd like to know what are your thoughts on the next big thing in quantum ML? Now, I mean, I know that we know that it's a very new field, and we're still working things out. But where do you see, what direction do you see this taking?
So maybe I can share my thoughts. So obviously, generally the goal is to get these fault tolerant quantum computers. So it's hardware limited, and we still have this question of what to think about in the near term with the noisy devices. There's a variety of different areas that are very exciting. So there's of course quantum machine learning, but there's also quantum chemistry. So this is kind of linked, and you end up still having a circuit with some parameters that you can train. But instead of the goal being, say, classification or some machine learning task, it's to find chemical properties of an input molecule. So you might end up finding, so that the energy ground state of a molecule. It still can use sort of machine learning primitives and still can interact with PyTorch. But that's, I think, one of the most exciting near-term sort of applications of quantum variational circuits. And there's still a lot of open questions there on what are the best practices, really. So what's the right circuit that we should use? What sort of gates? How can we efficiently measure the chemical properties that we need to minimize? You're muted again.
Well, I was just saying, thank you so much for your presentation and your answers today. This has been really enlightening, honestly, and I'm sure many of our viewers are really excited. If they were not super familiar with quantum machine learning, I hope they are now and excited enough to check out PennyLane, the docs, and also the tutorials. I know that I'm going to go and run some notebooks on this. Thank you so much. Is there anything that you'd like to say to our viewers, maybe how they can get more involved with PennyLane outside of the community calls and code togethers?
So maybe and I think you just alluded to this when you said notebooks, but one of the best resources we have for getting into quantum machine learning and quantum computation is the demo section of our website. So if you go to PennyLane.ai/QML, we have a selection of tutorials and demos there. And the demos are kind of self-contained. So I think they're categorized into different areas, but we have a dedicated beginner section as well. And what the demos do really nicely is they try and introduce the concepts with code as a tool to try and show you what's happening. So rather than just throwing equations and concepts, you have to actually execute the code and see what it looks like in practice. So the demos are a really, really nice starting points for getting familiar with quantum machine learning.
One final request Alan has is if the slides could be available publicly. If you are able to make this available, I can definitely link it to the YouTube description. And we'll keep you posted, Alan. Please, we'll notify you with the URL maybe. All right.
Yeah, we should be able to do that.
Perfect. All right. Thank you so much again for joining us today, and we'll be meeting again next week at the same time. Not yet has a question, but not yet. Maybe we are close to time now, so maybe we can get back to you on the answer for this in the YouTube comments, probably. It's a pretty broad question, I'd say, but all right. Thank you so much, and have a good day.
Thank you. Great to see you.
Thanks, everyone.